In this video, I'd like to talk about voltage sources in series. Very often, when we're dealing with circuit analysis, we have a very large circuit that looks complex. However, if elements are in series or in parallel, they might be able to be combined. If they're combined into a single equivalent element, then it will simplify the circuit by virtue of reducing the number of components we have to consider. This is often very desirable so that we can start asking questions about currents and voltages that are unknown in that circuit without having to analyze the entire thing all at once. The first thing we're going to look at is what happens when voltage sources are in series. And let's take a look. We'll start off with a bit of an example and be sure to keep in mind what happens to the voltage sources as we analyze this circuit. Now, I have a current through my resistor, and because it's a resistor, I have the positive and the negative as shown there. I'm also going to choose this node here to be my reference node. Now, a common question we've seen in this course so far is what is the current through the resistor? And remember, in previous examples, we've seen the question asked in terms of, is the current too high? Is there too much power flowing through the resistor? Sometimes we might even ask, is there enough power flowing through the resistor? Say the resistor is a light bulb. Is the light bulb bright enough? In order to answer that, though, I need to use KVL and Ohm's law. Let's use KVL and let's take a look at what happens to those voltage sources. First of all, I'm going in a loop this way. Notice that if I'm doing that, my two voltage sources are in series. They share this current I. So by KVL, I have 10 volts plus 20 volts minus VR is 0. And what we really want to know is what happens to these. Well, I just add them together, don't I? I get 30 volts equals to VR. Now, this might not sound amazing to you, but what we did was essentially take these two voltage sources and turn them into a single voltage source with a different value. In other words, I might be able to redraw this circuit as follows. With a 30 volt source and VR. Now, I did say what is the current through the resistor. We know that the current is equal to VR over R. R, though, was chosen to be 1 ohm, so my current is 30 amps. As I said in the previous video, that's quite high. I chose this value of the resistor so that the numbers would work out and be nice in whole numbers. But please be aware that 30 amps is quite a significant amount of current. Let's compare these two circuits. In the top circuit, I had two voltage sources and a resistor. In the bottom circuit, I have only one voltage source and a resistor. We can see, for example, that I don't need to use KVL here. I could just analyze the circuit by saying, well, the voltage source and the resistor are in parallel. Therefore, VR must be 30 volts. I didn't need to form the sum of the voltages. The other thing is, I could look at this circuit and I can simplify it because I don't have two more voltage sources. I have only the one. Let's generalize this and see what we can do. The general rule is as follows. Voltage sources in series add together. To make a single equivalent VEQ. What I would like to do is unpack what I just said there, because you're going to be hearing the word equivalent a lot. What does equivalent mean? In what sense? Well, in the sense above, I found that VR was 30 volts, and similarly, the current was 30 amps, whether I used the original circuit or the simplified one. That is what I mean when I say equivalent. Some of the circuit variables do not change. They're equivalent with respect to VR and with respect to I. They are not equivalent, however, as circuits. Why not? Let's take a look at something practical. If I were to actually build this, very, very often we have to use multiple batteries. Let's say that I have a remote control that uses 2 AA batteries. Physically, I do apologize for the drawing, these are my 2 batteries. How they're connected is as follows. This is 1.5 volts, and this is 1.5 volts. And then this would go to a generic circuit element, perhaps my remote control. What this would look like as a circuit diagram is this. My remote control is still here, and these are 2 batteries, 1.5 volts and 1.5 volts. Now, we've just learned that voltage sources in series act as though they are a single voltage sources added together. So I could draw this circuit as follows. From the perspective of the RC, the remote control, I see 3 volts. However, I just told you this circuit was actually built out of 2 physical batteries. Not a single 3-volt battery, but 2 1.5-volt batteries. So in that sense, it is not an equivalent circuit in the sense that they are interchangeable. I can't go to the store and buy a 3-volt battery. I still need to use these 2 batteries. So, why would I do that? When I'm specifying the circuit, I might specify a particular voltage and then try to build it using series voltages. Let's go back to this example. The person manufacturing the remote control might say we need 3 volts. I would be the circuit designer and say, well, I can't get a 3-volt battery, but I can get 2 1.5-volt batteries, so I can build up an equivalent voltage source using readily available components. The other reason we would do it is to simplify a circuit. Specifically to reduce the number of components under consideration. Now, let's take a look at a slightly more complex example and see what happens when the circuit is oriented in a way that doesn't obviously show that things are either in series or can be combined. So in this case, I might have a strange circuit for you. And let's put in another resistor here. Let's say this is a 1 ohm resistor. This is a 2 ohm resistor. And I'm going to say this is 10 volts, and once again 10 volts. Now, what I want to do is simplify the circuit. We'll learn later that we can also combine the resistors in a particular way. Since we don't know how to do that yet, we're going to leave them on their own. So in this case, when I say the word simplify, what I mean is combine the components as much as I can, given the knowledge that I have. We've learned how to simplify by combining voltage sources, so let's see what happens. The first thing we need to be aware of is the fact that some of the voltage sources are oppositely oriented compared to the others. Let's take a look at what I mean. If we go in a loop this way, as we often do for using KVL, we would increase by 10 volts by going from the low voltage to the high voltage. but then we decrease by 10 volts by going from high to low. And once again, we decrease from going to high to low. So the voltage sources would add together as positive 10 minus the first 10, that's this one here, minus the second 10 volts, that should not be a double minus, to give me an equivalent VEQ that is equal to negative 10 volts. So now I can draw this in. What I'm going to do first is keep my polarity upside down. If I draw a plus and a minus this way, then this will give me negative 10 volts. This was my 1 ohm, and this was my 2 ohm resistor. If you're happy dealing with the 10 volts, that's fine. If you'd like to work with it as a positive value, you have to reverse these two. What that would look like is this: a negative on top, a positive on the bottom. 1 ohm, 2 ohms, and now positive 10 volts. What are we really saying? That this terminal is at the low voltage and this one is at the high. Which means a convenient choice of the reference might be here. But it's up to you, as long as you're consistent. And that is how you combine voltage sources in series.